Okay, so now we're in our RStudio with our R code, working our way through our analyses. When we've just completed the independent samples t-test on programming time taken by students using Eclipse and Visual Studio, as we can see in the box plot here. And we've just covered our distribution assumptions, or our distributions and the ANOVA assumptions. And so now we're going to see how do we go about testing some of these assumptions, namely the normality assumption and the homoskedasticity assumption, the homogeneity of variance assumption. Remember, the first assumption was independence of our measures, and that's validated just through sound experiment design. That's not as much a mathematical test. So let's test our ANOVA assumption, starting with a Shapiro-Wilk test. It's a common test of normality. And we'll first start it on the response. But then, as I said, technically we want to meet the assumption on the residuals, which is the difference between our observed measures and the predictions of the statistical model we use. So we'll test it on for normality on residuals as well. So we can run this test, and a significant result indicates a departure from a normal distribution. And we can see down here in our output that for the Visual Studio data, we do have a departure from normality. And we can go ahead and also do the same for the Eclipse data and see that we have a departure from normality there as well. Now I want to highlight that these tests should be thought of as guidelines. ANOVAs, in fact, are somewhat robust to mild departures from normality and violations of homogeneity of variance. And also, how many data points you have influence these tests. If you have lots of data, you have a more powerful test. It may find that the data is not, that the result is statistically significant for the Shapiro-Wilk test, meaning the data is significantly different. But that might just be because you have so much data. So you just want to take these kind of with a grain of salt here. Now, let's actually test the residuals, as I said. So we first fit an analysis of variance model with the AOV function, and store that model in M. That's a common design pattern with R, is to kind of have models from these fitting functions stored in M. You'll see that throughout. And then we do a Shapiro test on the residuals, and we can see that also is significant and therefore a departure from normality. What can help us visualize this is what's called a QQ plot. And we can use two commands here to put a line through a QQ plot and see that in the upper portion of the plot, there's pretty big deviation from this line. This line represents what would be conforming the residuals to a normal distribution. So for all these reasons, we can be confident that, in fact, the time variable is probably not normal. And if you recall our distributions on the glassboard, we used task time as an example of what commonly is log normally distributed. So to test that, we're going to use another distribution test called the Kolmogorov-Smirnov test, or KS test. And we will try to use this test to see if log normality is a better fit. We'll load the mass library and do a fitting function on the Visual Studio data for the log normal distribution. We'll store that in fit and then run a KS test for the log normal distribution using the parameters we extracted from the fit, the mean and the standard deviation. We can see in our result down here that, in fact, the p-value is not significant, meaning that, in fact, we don't detect a significant departure from log normality. Given this is a time measurement, that's not so surprising because we know task time like this can fall log normally, but it's nice to confirm it. We've just done the same test now for Eclipse, and we see, in fact, also a log normal result is somewhat confirmed here. Again, you can't prove with a statistical test that these data are exactly log normal. That's not what this means. We're just showing that it's not a significant departure from a log normal distribution. So that's our distribution test for the assumption of normality. Let's look at a test for the homogeneity of variance. And for that, we'll use Levine's test and a variation on that called the Brown-Forsythe test. I've loaded the CAR package, and Levine's test takes our formulation of our model, time by the IDE, which is the programming language and development environment we're testing, And when we run Levine's test, we can see that we have a significant result, which means that we have a violation of homogeneity of variance. And in fact, if I go back up to the top here, just for a moment to reissue our box plot, I could also use the back button, I suppose, in the viewer there, the graphs. We can see that the variance of the two conditions is obviously looking fairly different. The Brown-Forsyth test is preferred because it uses the median rather than the mean and is a little bit more robust to outliers as a result. So that's what we'll be using from now on. And you can see it confirms that we have difference in variances here. When you have difference in variance like this, then you actually can, in the case of a t-test, use something called a Welch t-test. We indicate the variances are not equal in this var equal parameter. And by doing that, we don't have to conform to the assumption of homogeneity of variance, that third assumption of ANOVA. And when we run that t-test, we see, in fact, a significant p-value with an adjusted degrees of freedom that has a decimal now, has a fraction in it, and the t statistic. We know how to report that from our prior conversations. And we can see that, in fact, we see, according to that test, there is a significant difference in programming time by IDE, which the box plot visually would suggest. But the Welch test doesn't solve the violation of normality, just that homoskedasticity violation. So let's go down and take a step in data transformation. We're going to transform our data so that it conforms to the normality assumption. So here we are looking at the possibility of transforming our time data from our programming tools so that it complies with the assumptions of ANOVA. We're going to do that by creating a column in our data table defined as log time. You may recall that the KS test indicated that we may be log normally distributed. So we'll take the log of time and make a new column with that $ operator there on IDE2 called log time. And after I make new columns like that, I like to view them to verify that they're in the table. And in fact, we now have a new column called log time. I know it's small for you to see, but it's that last column on the end there. And we see that over our 40 subjects. Okay, so now let's give ourselves a little more intuition, this time around log time. So we'll see some histograms, and that looks more normal now, doesn't it? Normally distributed. Here it is for eclipse. Not quite normal, but it seems closer than before. And we'll do our usual box plot again as well. And now we can retest for normality. So we'll again do the Shapiro-Wilk test, this time on the Visual Studio data, and we can see what was significant on time is no longer significant on log time, indicating we don't significantly deviate from a normal distribution. And the same for the eclipse level of our factor. Now we know we should test on the residuals, so let's fit an analysis of variance model, which is log time now here instead of time. And let's do the Shapiro-Wilk test and see that, in fact, the residuals don't depart from normality at a significant level. And when we graph, we can see we still have a little bit of departure in the upper right corner, but it's not as severe, certainly, as before. And again, ANOVAs are somewhat robust to mild departures from these assumptions like normality. Okay, so we can also then reissue our test for homoskedasticity, just to make sure we haven't changed anything there. And it's close, but we're still we're now compliant actually with our homoskedastic assumption. So we can issue our t-test this time with the var equal being true. We could still run it with false and do the Welch test if we liked. The results are very, very similar. The conclusions certainly don't change for that. And here we have a significant p-value, but now one that we can trust a bit more because we've transformed our data.